Yeah, sounds good. Hello, everyone, and thanks for joining for the fifth week of the MTV Nuclear Engineering Summer School. Today, happy to welcome PhD student Ricardo Lopez with the Detection for Nuclear Nonproliferation Group here at the University of Michigan. His main advisor is Professor Sarah Pozzi, and he works on radiation imaging with his dual particle imager, which hopefully we'll hear about a bit at the end of this lecture. But he'll be talking to you today about radiation imaging methods. And Ricardo, I'll hand it off to you. Thank you.
All right. Thank you, Flynn, for that. Everything looks good on my front, so I think I'm just ready to get started then. So, hello, everyone. My name is Ricardo Lopez, and today's lecture is going to be on radiation imaging methods. And specifically, I'd like to start off by talking a bit about the motivation for using imaging systems in general, but specifically with respect to nuclear proliferation and nuclear safeguards efforts. So one big area of use for said imaging systems could be in search and emergency response scenarios. So currently, there's a lot of deployable equipment or detectors out there that will measure relative count rates or dose rates in a particular area. And by using certain search patterns as the users, you'd be able to figure out based on the general readings that you're getting in an environment where a source may be situated at, for example. However, that kind of approach could be very time consuming and also not very accurate. And generally speaking, for a lot of these search and emergency scenarios, time is quite literally of the essence. So being able to quickly localize a radiation source would be quite paramount. So imaging systems in this case could be a very powerful tool. Not only can they be essentially designed to be not as sensitive to background radiation, but they can also be used to get a general sense of the direction of your radiation source if it's confined to a particular single source in, say, an environment. Another popular application for imaging systems would be for verification purposes. Specifically, to give you a concrete example, would be, say, for treaty verification efforts. Generally speaking, inspectors will be attempting to monitor or verify the presence or absence of a radiation source. And this may be happening in a particular facility where certain rules may be in place, where they may or may not be able to enter certain areas or may not be able to open and close certain containers. So inspectors have to make this call with a high degree of confidence, and they may want to deploy passive systems that would be able to effectively reach set goals. And in this case, to consider an idealized imaging system in this kind of verification case would be one that is of small footprint, such that it's actually portable, and also low power, so that it's not a significant burden to actually use and deploy out in the field. To begin with, for this talk today, I'm just going to give a brief overview of general radiation imaging methods. Also, to preface what exactly I'll be specifically highlighting for this particular talk. In general, nuclear imaging methods that are employed out in the field with respect to safeguards applications can generally be classified into one of these three categories. You have transmission imaging, which is where you use an external source and basically detect the attenuation of the emitted radiation as it goes through a particular material or object of interest. You have emission imaging, which is where the source or object itself emits the radiation, and then you passively acquire or detect that. I'll note that for this particular talk, I'll mainly be focusing on this category of imaging, specifically with respect to neutron scatter cameras and Compton camera imaging methodologies. And then finally, we have induced emission imaging, which is where radiation is induced within an object or source using an external radiation source. Now, this is just, broadly speaking, three general categories that could be used to classify the kind of imaging methodologies used. However, there are numerous other kind of methods that could be employed, and not just in nuclear safeguards, but other applications, such as, to give you an idea, nuclear science or medicine. We have, of course, SPEC, PEC, nuclear neutron tomography, CAT, and a whole lot other imaging methods. But again, for this particular talk, we'll specifically be focusing on the two scatter based ones with the neutrons and the gammas. So to begin the introduction to the neutron imaging, specifically using neutron scatter cameras, suppose we have the scenario where we have a neutron emitting source and that we have an incident neutron hit, say, one detector volume, in this case, denoted here by these three particular parameters that we obtained from this first scatter. When a neutron elastically scatters, say, in this detector volume, we'll be able to obtain certain pieces of information. Namely, we'll be able to get the energy deposition, the location in which the scatter occurred at, and the time at which that scatter occurred. Then, if that same incident neutron, after scattering off, say, this first detector volume, as goes along its way, if it then happens to hit another detector and then undergo a second scatter, then we again have a secondary set of the same kind of metrics as before, i.e., energy deposition, location, and time. And for a neutron, when you have these pieces of data, then you can start doing some pretty interesting calculations. Namely, you get the velocity of the neutron as it travels between the two interaction locations. You can do this since you have both the positions in space and the time difference between said collisions. And then using the velocity of a neutron, you can calculate its kinetic energy, or in this case, for this context, it'll be the energy at the time of flight. So it'll be whatever the neutron's energy was after that first collision as it's traveling onwards to where its second scatter will ultimately happen. Once you have this energy time of flight, then if you add it to the energy deposited in the first event, then that should equal the initial energy of that incident neutron. And then using certain kinematic properties that I won't go into in this particular talk, you can relate the energy time of flight with the total energy of that neutron to get a cosine squared of theta, where in this case theta is the angle of incidence for that neutron. And if you use certain projection methods, then you can have an idea of where in space that neutron originated from. And as you can imagine, if you measure for a long period of time and acquire enough statistics, enough of these cones should intersect somewhere in space, and that would tell you where the most likely location for your source would be in that case. For gamma ray imaging, or using the Compton methodology, it's a very similar process. Say we have the scenario where we have an incident gamma ray, and we'll have a Compton scatter, in this case, off one detector volume. Again, we get the same metrics as before. We know the energy deposited in the event, the location, and the time. The difference here is that for its second interaction, instead of undergoing, say, another Compton scatter, we'd like it to undergo photoelectric absorption, such that if you were then to add the two energies deposited between these two events, you should get the total gamma ray energy for that incident gamma ray. And then using a similar kind of idea or process as discussed before, by making use of the kinematic properties of this process, you can essentially figure out, again, what that incident angle for the gamma ray was. Before, with the neutrons, it was a very straightforward ratio, if you will, between the energy time of flight and the total energy. This time, since for gamma rays, it works a bit differently, the subsequent equation is slightly different, but we, again, still collect all the necessary metrics during the measurement. Thus, we could still calculate the same opening, or rather the incident angle for that gamma ray, which is in accordance to that, the opening angle for the cone in which we are, based on the math, assuming that that gamma ray originated from somewhere along this cone in space. I will note that generally speaking, you have no way to necessarily guarantee that the second event in, say, detectors two's volume is actually photologic absorption, because there's other interactions that are competing at the same time at any given energy for that gamma ray, as you may have heard from one of the previous lectures in the summer school with respect to gamma ray interactions. However, what you can do is you can place an energy gate on a particular energy of interest that would correspond to the photo peak of interest for a particular source. That way, if you're gating on that summed photo peak in the coincidence spectrum, then you can assume that the following sequence of a Compton scatter in the first interaction and a photological absorption in the second interaction holds true. Though in order to do so, I will note that you have to make sure that your system has time resolution that is good enough to resolve these events, of course. Once you have all this data and have all these angles, what can you actually do with that? Well, what you can do is take these cones and project them onto a surface such that you can actually add them or sum them together. And this process we'll call, in this case, simple back projection. And to give you an idea of what that would look like, this little video that's playing on this slide is giving you an idea of a one measurement that we took with an imaging system. And as we add more imageable events, i.e. cones, then you can see that slowly but surely we do end up converging at a more precise location according to this heat map that you see on the looping video. You can also note that when we have a low number of cones, or rather low statistics, that this hotspot is not very well defined, and it's also shifting pretty significantly within this field of view that we're displaying right here. And what I'm essentially demonstrating here is that as you get greater amount of statistics or imageable events, you end up becoming more and more confident in the final converged location of wherever your radiation source may be present in this kind of space. Next, I'm going to talk about, mathematically speaking, how we're actually doing that simple back projection process. I mentioned before that we're taking these cones and projecting them onto some kind of surface of which so that we can actually see the image. In this case, let's take the surface to be the surface of a sphere that's centered around our imaging system, and we'll have the imaging system be oriented such that the center of it corresponds to our origin point of 0, 0, 0 in Cartesian space. What you can then do is take this spherical surface surrounding your imaging system, and then essentially you can break it up or break it down into a 2D matrix that corresponds to azimuthal angles and altitude angles on the spherical space. Then what we want to do is project these cones in Gaussian space, since again, our metrics or our data have inherent uncertainties associated with them. We don't know with 100-degree certainty on any one of their particular values. And then as that error propagates throughout some of these calculations, that basically ends up being visualized in the form of these cones having thicknesses and broadening, which is in this case handled by this Gaussian approach. We have the position of a pixel on the spherical surface. We can basically convert the spherical space over to Cartesian space so that the calculations are a bit more straightforward. And similarly, the vector between interaction locations of our particles, we will call in this case our lever arm. The actual angle between the lever arm and any given pixel on the surface of this sphere is given by this one particular metric here, beta sub b. The sub b is there because this is going to be calculated for every single pixel on the spherical surface. And I will note that as I'm talking about this mathematical approach here, this particular step with the beta term tends to be the most abstract. In this case, the best way that I've been able to try to convey what this actually entails is that it's basically getting the contribution of every individual pixel within this spherical projection surface, such that it's not quite a probability, but you can think about it as such, where pixels with high values or intensity values essentially represent a higher probability that that's where the source or particle in this case originated from. And because, there's uncertainty with our data, we're not going to be able to find an infinitesimally thin or small cone on this surface. It's going to be broadened such that technically speaking, every pixel on this surface contributes somewhat to the probability of the source being there. And then finally, and the more intuitive particular parameter here is alpha, where alpha is equal to the cosine squared of the incident angle of your particular particle, whether it be a neutron or gamma ray in this case. And here I'm showing it to be equal to the ratio of the time of flight over total energy. Again, this would only be valid, say, if we're dealing with imaging a neutron. The actual equation would be slightly different if it was a gamma ray, but it still holds true that what we are calculating is this cosine squared theta term for the scattering angle of the particle, which will ultimately end up becoming the opening angle for the cone in which we're projecting. And then finally, the actual cone projection is hindered by this Gaussian-like distribution or function, rather, shown down below, where we have the beta term, the alpha term, and then the sigmas represent the uncertainties in those two particular parameters. So I know I just went through a lot of math, so to speak, so things may not be quite concrete in terms of what's actually going on. So I'm going to use the next couple of slides to go through a couple of very simplified test cases to basically show how the math works out and what the ultimately what the visuals or the cones would look like. So here we have a particular scenario where right now this figure that we're seeing in the middle of the slide, we're looking at it from a top-down view where the out of the screen in this case would be the z-axis, but left to right would be our y-axis and up and down would be our x-axis in this case. I'm saying that, say, hypothetically, we have two different detector volumes that are these cubes in this case, and we have a first scatter that occurs in this particular location. We'll call x0, and then this second vector x1 shows the xyz coordinates of the second scatter, i.e. the scatter in the second detector. I'll also tell you that the alpha term or the cosine squared theta term is equal to 0.5. And I'm also saying that we're going to be assuming 10% uncertainty in this alpha term and then the subsequent beta term. If you were to plug in all these numbers into the equations from the previous slide, and you did this on every individual pixel of the projection space, then the resulting cone that you would get is shown here onto the right in this spherical space, where we have it centered basically level to the system. But what I'm highlighting here with these white dashed lines is that they are all at 45 degrees. And the reason for that is because based on the numbers that I just described, the incident angle for that particle would be 45 degrees. Hence, the opening angle of the projection cone would also likewise be 45 degrees. Cool. And then I'm also showing surrounding the detectors this red ring that's marked with certain azimuth angles. That's the particular frame of reference that I'm using for this particular test case. So we can see that off into the positive x direction or directly ahead of detector 1 would be an azimuth of 0. And then based on how the incoming particle came, that it should be coming from that general direction, which is why the cone itself, it has an opening angle of 45, yet it is also centered at an azimuth of 0 in this case. This time, similar test case as before, I literally just changed one thing, which was the location in XYZ of the second scatter. Otherwise, everything else still holds true. Based on the figure, though, you could see that now the incident particle came from the 9 degrees azimuth direction, hence why the corresponding cone now it still has an opening angle of 45. That could easily be seen by the fact that the alpha term is still 0.5, i.e. hasn't changed. But now it's just shifted from being centered at a azimuth angle of 0 over to a positive at 90 degrees, which in this case will correspond to the right-hand side of the two different detectors. Now, for a more interesting or less, I guess, less intuitive test case, we still have two detectors in this case, except they're stacked on top of one another, which is why in this case you're only seeing the one cube. However, the two scatter locations are basically just happening along a line, in this case along the z-axis, but everything else holds true. What this would mean is that the cone still has a 45-degree opening angle, but the resulting projection is going to look a bit weird if you basically aren't very accustomed to seeing a lot of these spherical-like images in this spherical coordinate space. Here, I'm showing the resulting cone is actually just a vertical, or rather, sorry, a horizontal line in this case at 45 degrees. The 45 degrees should make sense since that is the particular opening angle of the cone. But the reason it happens to lie along all azimuth angles, as you can imagine, is if you have the two detectors that are stacked atop of another, and based on the XYZ coordinates that I gave for the two scatters, basically what's going on is that the incident particle is coming directly from above. And in spherical space, that would correspond to just, a horizontal line, since it is a cone that would be directly above you, but as you unfold it, as you can imagine, you would just have a straight line rather than a circular cone, enclosed cone in this case. Cool. All right. So these next couple slides are just going to be going over some of the properties that you end up facing when you're doing a lot of these cone projections while holding certain things constant and other things variable. In this case, these results were obtained using simulations just to make sure that everything that needed to stay constant did, and that the things that I wanted to highlight were actually variable. In this case, on the left column, what I have here is showing what happened where everything else being constant or the same, what happens to the cones as your relative uncertainty and your parameters increase. At the topmost one, we have the case where we have about 10% relative uncertainty, which in most cases you can think of as pretty good in terms of uncertainty and actual measurement. Right below it, we have 50% relative uncertainty. And then at the bottom, we have 100% relative uncertainty. The most noteworthy thing that you should be able to pick up is that the thickness of the cones themselves is increasing as the uncertainty increases, as you can imagine. If you're less certain in your initial parameters that are used for this projection, then obviously that just means that you are less certain to a more exact degree in terms of where your source may lie along the cone. So as a result, the cone has to be a lot thicker in order to take that into account. Meanwhile, if we have everything else being equal, but our scattering angle is what changes, starting from the top, we have 25 degrees, 45, and then 60. And we can see that the cone thickness is getting smaller and smaller. Essentially, what I'm trying to get at here is that high scattering angles would be preferred for imaging applications, since they tend to give you the best metrics or data, if you will, for the converging of a particular radiation source. However, having high scattering angles may not always be feasible depending on your system design, but also depending on certain parameters such as like for example, the energy of the radiation being emitted by a particular source. High scattering angles may not be very likely at certain energies, for example, or depending on the actual setup. Another thing that I wanted to show was essentially what happened. I showed you, let me go back to this one slide real quick, what's happening on an individual event basis or on a per cone basis. But generally speaking, you're not going to be looking at individual cones. You're going to be looking at the quote unquote final image or the summation of all the cones that you have in a particular measurement. And so to better illustrate then what the effects of the uncertainty and the scattering angles are on the more final images, then here we have, again, a simulation of a couple thousand imageable events. And the corresponding full width half maxes represent, in this case, a rough metric for how well converged a image is with respect to the final converged location. And as we could see on the left column for when we're changing the uncertainty ranges, the top image consists of imageable events that have anywhere between 10 to 100% relative uncertainty. And as you go lower and lower down the column, then this range of uncertainties basically narrows, i.e., I'm basically having it be more constrained to a particular range of actual uncertainties, such that on average, the average uncertainty is a lot lower as you go down the column. And generally speaking, if you look just at the full width half max values, you could see that they are getting smaller, so therefore you are getting a more converged image, i.e. a better result. Visually speaking, it's kind of hard to see much difference between the top and middle, but if you compare the top and say the very bottom one, you could see that the biggest impact happens to be in this green region surrounding the very, very dark red hotspots. That green region is a lot less at the lower average uncertainty set data set. And so that would be fairly beneficial in certain cases, namely when you may not have as high statistics as you do in this case, where even though you have this fairly large-ish blob, if you will, of semi-high intensities in this case, it is still fairly evident that the true converged location would be at this very dark red spot. But again, this is because we have a high degree of statistics in these cases. If it weren't the case, then it may be more fitting to have, say, data that closer matches the one on the bottom, since it would be more closely converged to the actual source location. Similarly, when we restrict the possible range of scattering angles, we could see that if we have anything from 10 to 170 degrees, we have the image on the top right. But as I constrain the range of possible scattering angles, then we could see that the corresponding simple back projected image changes accordingly. And both by visually comparing the three images on the rightmost column and also comparing the full width half max values, you could see that compared to the changes that I did with the uncertainty ranges, changing the scattering angle ranges had a much more significant impact on the final converged images, or rather just how well converged the images got. And that's just another thing to note. If you had to pick between having very low uncertainties versus having a very constrained scattering angle range, you probably want to go with the scattering angle range if feasible. The reason this may not be the case is confining it to a very particular scattering angle range oftentimes basically means you're only accepting a very small subset of your total data that you collect during a measurement. And depending on your measurement time, it may just not be feasible to wait long enough to, get enough statistics within a small particular band of scattering angles in order to make a final image. So there's a lot of give and take or optimization that would have to be done in part of the user for some of these analyses. All right. Next up, another important factor that basically affects the quality of the images that you may end up getting via simple back projection is your lever arm distributions. As a quick note or reminder, what I mean by lever arm is basically the vector between the two interaction locations of your particle. And if you were to map these lever arms in 3D space, then you get these kinds of tendril distributions that you see in this top right plot. And then the corresponding simple back projected image that you would get from this kind of data that has this particular lever arm distribution is shown on the bottom. And as you can see, it is fairly symmetric, well converged, and is, for all intents and purposes, a pretty good image. What I'm going to be showing you in these in this next slide, though, is what happens when you vary the number of lever arms that are available to your imaging system, and then what the corresponding effects are on your simple back projected image. At the top, we can see what happens when we have a very small number of liver arms. Based on the image that you see on the right, you can see that we have these very significant artifacts in the images. You have a lot of distortions as well. Essentially, what you can see as you increase the number of liver arms in your liver arm distribution, you can see that your simple back projected image gets less and less of these very drastic artifacts and ends up becoming more symmetric overall. Uh, Basically, as you increase the number of lever arms, you end up getting more symmetric and more smooth simple back projected images. However, I will note that even though you may have the same number of liver arms between two said, say, for example, imaging systems, it's the way that they're distributed would also have a significant impact. So in this case, I have the case where I did two different simulations, one where the liver arms are fairly uniformly distributed, and then another where you have these very clear two different lobes, if you will, one off to the left, one off to the right for the liver arm distributions. And then we can see that while we do maintain the same number of lever arms in this case, the effects on the simple back projected images are quite drastic or different from one another. Again, the one that's more symmetric in terms of the lever arm distribution has a more symmetric simple back projected image, while the one on the right, which is the one where they're clumped up into two distinct groups, you can see this elongation in the attitude angle direction, which would not be ideal to have for an actual measurement. To better illustrate what's actually going on in the previous slide and why the way that the lever arms were distributed and why that matters to the final image quality, I'm going to give you an example of a fairly simplified and very extreme case of lever arm based distortions. In this case, we have this scenario where we only have basically a single lever arm distribution as shown to the top right. We have the left clump that corresponds to forward scattering events, and then the one to the right that corresponds to back scatter ones. Generally speaking, you're left more forward scattering ones. So if we have this if we have all the lever arms essentially lined up here on the left on this blue line, and you pick a point on this distribution, in this case indicated by these red points, what you'll have is you'll have an imageable cone that is centered at that red point and then has some opening angle or scattering angle that's just, that depends on whatever energy was deposited by your particle. But you could see that if we, in this case, had a true radiation source placed somewhere, say at z equals 0 along the z-axis, then no matter where you go along this blue line, in terms of having a cone centered on it, if all these cones are indeed real and did originate from a particle that came from this yellow star, then they should all intersect at that yellow star. But you can see, because we're only restricted to this vertical line, no matter what you do, you're going to end up having the fact that your cones are going to be intersecting one another on this kind of plane at 0. So the corresponding simple back projected image would look like this, where you have extreme distortion and elongation along the azimuth angle. And it should be a bit clearer, easier to see why that's the case, as you see how all these cones are actually intersecting with respect to one another in this particular simplified scenario. All right. So that concludes the talk in terms of discussing some of the methodologies, applications, and some of the mathematical theory behind scattering methodologies with respect to neutrons and gammas, i.e. neutron scatter cameras and Compton cameras. What I'm going to be talking about next are some more concrete applications, examples which are used in research. And in this regard, I'll be talking about my current research as far as the PhD program here in the University of Michigan. I've worked on developing and building a imaging system pictured here. It is called the Handheld Dual Particle Imager, or HDPI for short. This imaging system is not a single detector. It's actually an array of multiple volumes of detectors. Specifically, it's composed of 12 organic glass bars that are wrapped in Teflon for light output collection. In terms of dimensions, we're looking at bars that are 6 by 6 millimeters cross-sectional area and 50 millimeters in length. So in the grand scheme of things, quite small, quite tiny and small in volume. In addition to the 12 bars in the system, we also have 8 cerium bromides. These cylinders are likewise 6 millimeter diameter, 6 millimeter height, and they are situated at the 8 corners of the active volume, as demonstrated in this like little looping video on the right of the slide. Uh, what I will note regarding the bars themselves, the material that they're made out of is OGS. This stands for Organic Glass Scintillator. And as you've probably heard in previous talks earlier in this summer school, um, scintillators, the way whenever they interact with radiation, they respond by emitting light or scintillating light. So what I'm doing with this imaging system is I'm collecting this light from the events at the top and bottom end of the bars using SciPM arrays. I will also note that for OGS, one of the main reasons we're using it is because this particular composition is able to discriminate between neutron and gamma ray events based on the resulting pulse shapes that you get from the interactions along the bars. You can also probably note that due to this dual-ended readout design, whenever I have a single interaction in one of the bars, I don't get one signal. I actually get two. I get one from the top end and one from the bottom end. And this is important because it allows me to do position reconstruction along the z-axis, such that for when it comes to simple back projection, I'd be able to get the X, Y, and Z position of an event along the bar. I get the Z position by comparing the ratios of the signals at the top and bottom ends. And then I get the X and Y coordinates based on the midpoint of the particular pillar or bar that the interaction happened to occur at. So by using this dual particle imager, we'll be able to collect data and create similar simple back projected images as I've shown in the past couple of slides. But we also, on top of simple back projection, apply a converging algorithm called LMMLEM to further converge onto a source location. And I'll be showing a bit about that in a bit. Here I'm illustrating physically what's going on with the HUDPI and how I'm actually performing the imaging. Say we have an incoming gamma ray, we'll ideally undergo a Compton scatter off one of the 12 bars, and then subsequently the gamma ray will scatter off and hit one of the 8 cylinders in the corners, and hopefully undergo photologic absorption. As I mentioned before, there's no guarantee that the gamma ray will undergo photologic absorption in the cerium bromides, but by placing energy gates at particular energies in the final data set, we can better guarantee that we do have this particular sequence of events occurring such that the gamma ray imaging methodology holds true. Similarly, for an incident neutron, all I'm looking for is for an elastic scatter off one bar and a subsequent elastic scatter of a second bar in the system. As long as it doesn't happen in the same bar, then we're good in this particular case. And again, if we measure for long enough, we get enough of these cones and they should all intersect right where the most probable location of the source would be at in the environment. I'm going to be demonstrating the capabilities of the imaging system using these 2 different experiments. One is a gamma ray focus experiment where I have 2 different gamma ray sources. The distance is noted here on the slide. Meanwhile, for the neutron-based measurement, I have 2 neutron sources and a third source that's a pure gamma source. What I'm going to be demonstrating here is that not only can the imaging system measure multiple neutron sources in the same field of view at the same time, but it could do so in the presence of, say, additional sources, say like a pure gamma source, and it won't make the misclassification of more than 2 neutron sources in this particular scenario. So for the gamma ray localization or imaging experiment, here's a look at the images when I place certain energy gates. For the left image, I place an energy gate centered at 511 keV. The reason for this is that one of the gamma ray sources was sodium-22, which has an emission at 511 that we would like to image in this particular case. The rightmost simple Bragg projected image, meanwhile, has an energy gate at 662. And again, this for a very similar reason. The second gamma ray source was cesium-137, which again has emission at 662, which would be of interest for us in this particular experiment. For these particular simple Bragg projected images, it's the result of the data collected within the first 18 seconds of starting the data acquisition. So I'm just showing here that even with such a small acquisition time, we're still able to have a general sense of where the sources may be situated at, as indicated by the circular outlines representing where the sources were during the experiment. However, if we measure for several minutes longer and then apply the converging algorithm that I mentioned before, then we end up with the final images shown here, where we have very good agreement between the true gamma ray source locations and the final converged locations according to the data collected. Similarly, for the neutron imaging results, here in the field of view, we have three different sources. But as you can see on the image shown on the right, only two distinct hotspots are apparent in this image. They correspond with the plutonium beryllium source and the California 252 source, which in this case are our two neutron sources. And then off to the right, an azimuth of positive 9 degrees, we did have a cesium-137 source. Again, though, this one is only a gamma emitter. So for a neutron image, making use of neutron data, you wouldn't anticipate to see anything in that general region. And indeed, that is the case that we see here with this image, where we see nothing off where the cesium was actually placed at, but we see very clear regions for our two neutron sources, which was, again, great to see. So what's next for imaging visualization? I've showed you some of these, and I can go back to this slide real quick. I've shown you an example of a result in the form of a neutron image and say a gamma image in this case. However, these particular images, again, are in spherical coordinates. So the way that you interpret them is that the x-axis is your azimuthal angle with respect to your imaging system, while your y-axis is your altitude angle with respect to your imaging system. And out in the field, it may not be the most intuitive thing in the world to actually be able to tell where a source may be present in a given environment based solely off, say, one of those 2D images. So one of the things that we had started thinking about a couple years ago was, are there any alternative ways where we can convey this radiation imaging information to users in another way, such that it is apparent to the user where a source is present in an environment in real time? And our solution to this question was, what if we try displaying or representing this imaging information to the user via mixed reality or augmented reality in that kind of environment, such that they would be able to visualize something in their actual space using the data collected from the H2DPI. And then on top of that, one of the other kind of caveats with, say, this kind of an image right here is that just based on the image that you see, you really don't get a sense for source to detector distance. You may have an idea of where a source may be at in the angular space, or in what angular direction may be relative to your system, but you don't necessarily know how far away, which in a search scenario or for a safety kind of oriented scenario, that is very important to know. So we were also trying to come up with a way to figure out source to distance information using said imaging system. And so instead of using simple Bragg projection, one thing you can do is using triangulation or 3D imaging methods by making use of multiple imagers at the same time. And I'll get into that in a bit. With respect to the mixed reality approach, we developed a pipeline where we have the detector system. In this case, it's the scatter-based H2DPI. And we have a data acquisition computer that takes in the raw data and then does all the necessary calculations to get the angular information, i.e. the projection cones. And then the real key to this process is making use of the Microsoft HoloLens 2. So this device is an augmented reality headset developed by Microsoft. And the most noteworthy thing about it is it has a lot of sensors in its front visor. that allows it to create a live spatial mesh of the user's current environment. So by combining the live updating spatial mesh with the projection information from the imaging data of the HoloLens, from the HDPI, we wanted to be able to visualize these heat map distributions in mixed reality space using the spatial mapping such that it aligns closely one-to-one to your actual environment. And so by making use of the double interaction events, separating them out based on particle type, and then projecting the cones, the user would be able to turn on the imaging mode capabilities of an application that we built, and then have a lot of customization options at their disposal, such as changing between neutron and gamma ray imaging modes, rendering the spatial mesh, displaying the 2D image, displaying energy spectrum information, and then, of course, being able to mess with the color options for the visuals to account for, say, certain types of color blindness. And for this particular topic, I won't have enough time to go through all of this pipeline in great detail, but we have published this work before that you are free to check out, and it will go into a lot deeper details regarding this HoloLens pipeline than I will in today's talk. But to demonstrate this HoloLens capability, I set up an experimental setup that's supposed to represent a mock inspection scenario. So in this case, say you are an inspector at a foreign country and you're at one of their nuclear facilities, and they bring out 3 barrels in front of you and tell you that they are basically declaring 3 neutron sources. And it is your job as the inspector to verify their claims without opening the barrels and being too intrusive with their stuff. And so for this mock setup, I brought out 3 storage containers. I brought out 1 neutron source in the form of californium-252, 1 pure gamma source in the form of cesium-137, and then I intentionally left the 3rd barrel, which in this case is the middle barrel, completely empty. And what I'm going to be showing you in the next couple of slides will be real-time acquisition of this particular setup, and then a final visualization of the sources distributed among the barrels. Before I do, I'm going to give you a bit of a reference in terms of what we expect to see in the form of the more traditional 2D images. In this case, on the left, we have the neutron image. As you can very clearly see, we have a very obvious distribution off at about negative 100 degrees azimuth, which again corresponds to the leftmost spiral as we would expect. We see nothing in the middle, which makes sense since there was no source there. And then we see nothing at about positive 30 degrees azimuth, which is where the rightmost spiral was, because again, there's a neutron image, so we don't expect to see the pure gamma source show up. However, then if you look at the right-hand side, for the gamma ray image, we have a very clear and obvious distribution over to the cesium 137's location. Nothing again with the middle barrel, and then nothing over by the californium-252 source. Normally, you actually would see some contribution from the californium-252 since it is emitting gamma rays. However, I did, for this particular scenario, heavily shield the californium to reduce its gamma ray signature drastically. And then the energy gate specifically was at 662 to mainly focus on the cesium. So that's why that's the only one that you really see in this particular example here. But here's a little video demonstrating how a user on the field would actually go about using this mixed reality process. Here, I'm taking the HoloLens, I'm placing it, and then in a bit, I'll swap over to my field of view, recording on the HoloLens. And right now, I'm just opening the menu and initializing and opening the application that we built to handle this visualization. It's based off of Unity, so it was fairly straightforward to get the rough implementation. And right here, as you can see, I'm scanning this QR code as I'm initializing the program. The reason for this QR code is that it serves as the anchor point in the mixed reality space, and it provides the correct frame of reference. Since without this QR code, your quote-unquote origin point in this mixed reality space would be wherever your head happens to be at when you open the application. However, since we need everything to be oriented properly and centered correctly so that the simple back projection actually lines up with where the data, or rather where all the frame of references are during the calculations. We basically place a QR code on top of the imaging system, which is what you would do, say, on the field. Here in this next video, I'm showing you real-time acquisition in neutron mode. And then on the top left, I'm indicating the current data acquisition time, or basically how long have I been measuring for in this case. And what you may be able to note is, as we have low data measurement times, i.e., as we have low statistics, the hotspot isn't very convincing anywhere. It basically will move around this barrel off to the left-hand side. But as we get more statistics and get more imageable events, come the, say, roughly 3-minute mark, we are fairly well converge and hitting that particular barrel. Thus, we would have some confidence in saying that there's probably a neutron source placed within that container. You can also note for this particular video that there's a lot of these white triangles, and that is the spatial mesh the HoloLens is generating. However, it is quite a lot of information and quite a lot of visual clutter, visually speaking, for from the point of view of the user. So one of the options that we have is that you can toggle this mesh off. So for the rest of the slides here, I'm going to have that disabled, such that the visuals are a bit more clear and a bit more obvious in terms of where the sources may be at. On the top right, I'm indicating what mode, imaging mode I happen to be at. And as I swap between my neutron imaging mode and gamma ray imaging mode, you can very clearly see that the corresponding hotspots and the end up appearing and disappearing at various barrels corresponding to the proper sources. In this case, when I'm in gamma mode, the right barrel is the one with the hotspot or the distribution as indicated by the green heat map. And then I'm going to bring up, in this case, the gamma spectrum, since again, on the field, it may be necessary, or rather it will be very useful for isotope identification to have an idea of the gamma ray emission. Similarly, for the neutrons, you can bring up the neutron spectrum. This one might be less so as useful, since you typically need a lot of statistics to get a fairly good idea of your spectrum shape. But again, the information is there for the user if it becomes apparent or needed out in the field. And one other thing that isn't apparent because this video is muted is that the HoloLens supports voice commands. So generally speaking, you could use your hands and to navigate these buttons or this user menu that's currently up on this particular frame. However, if your hands are occupied, say if you are using other pieces of equipment at the same time that you're running this measurement, then instead of having to put them down and navigate the menus to do whatever you need to do on the HoloLens, you can just use voice commands in order to achieve the same functions. So by just saying neutron, it would go over to neutron mode. By saying chart, it would bring up the energy spectra, for example. Cool. So that's the mixed reality approach as it currently stands. And then I'll close off today's meeting by just dropping, or rather talking a bit about some current future work that I have planned here within the group, which is mainly 3D imaging in voxelized space. So as we saw before with the simple back projection approach with the HoloLens, we are able to visualize source distributions in this mixed reality space. But again, the issue arises where we don't really have distance information. What the HoloLens application is doing is it's taking any and every intersection along the spatial mesh in a particular direction according to the imaging data or the cone projection data. That means if you have, say, 2 barrels that are in line to where a source may be at, both barrels, for example, would be lit up. So it would be kind of tough on part of the user to determine which of the 2 barrels actually has the source. So by being able to do 3D imaging, though, it would be more obvious, more apparent which barrel in this case, for example, would be of interest. So what we have done is, or what we are doing is we're working on an algorithm that makes use of data from multiple imagers or from the same imager, doing measurements at different spaces or different points in space. Excuse me. And we are able to, again, construct cones from the imaging data. But instead of projecting them onto a spatial mesh, we just project them and intersect them with a voxelized space in the mixed reality environment. And this can kind of be visualized with the figure here on the bottom right, where we have two different cones, one coming from each detector based on the data that I got from a radiation source placed right there. And if everything is working as intended, these like two cones in the voxelized space should intersect close to, if not at, the voxels near where the radiation source is present. So as you get more and more cones or imageable events, you should ultimately see a cluster of voxels with very high intensity values, and that would correspond to your most likely source location. And right now, it is currently a work in progress, and it hasn't been fully implemented in a live working version on the HoloLens, but we do have a couple of debugged versions that are work in, say, in like Python, for example. That's what this leftmost plot is, a 3D voxelized space plot of the Californium source in our lab, taken using two different locations in space of the two HUD that we have available. Over on the right is the experimental setup, but on top of it, I've overlaid a mixed reality render of the same data in this case. Again, this wasn't generated in live time, but you can visualize it in live time. It's just not actually being processed currently in live time. So we hope that in the near future, we'll have the necessary capabilities and further refine the algorithm so that we can do similar experiments as I've shown before with the mock barrel scenario with this kind of a 3D approach in the coming future. So I'd like to thank everyone for listening to my talk, and I'd be happy to answer any questions. Thank you.
All right. So it looks like you do have some questions. It is 2 o'clock if anybody has to go. Ricardo, do you have a few minutes for questions, or are you do you immediately have
Alrighty.
to walk out the door?
So we'd like to just go through the Q&A panel, Mairead, and then I can answer
Yeah,
the questions.
sounds good to me. So one of the first questions was, how do you differentiate between multiple incoming particles? Um, which I think refers to any pileup that you may see in your system.
Yeah. So that's a good point. I guess on the note of pile up, because I mentioned before that our scintillators themselves, their volumes are very quite tiny. Generally speaking, for most sources, I don't actually observe much pile up, if at all, just due to the generally low efficiencies of the system. In cases where it may be an issue, such as, for example, one of the cases where I have seen pile up with the imaging system was like when it was operating in the vicinity of a linear accelerator being operating, then you do have pile-up issues. But even with said cases, you basically would just rely on pole shape discrimination and time tags or timing properties of your events to be able to differentiate between events to the best of your ability. Because of course, at a certain point, you really won't be able to retrieve or differentiate between two events separated too close in time. And so you make do with what you can.
So I've got two related questions here, and I think I'll probably ask you both of them and see what your answer is. So the first one is, what's the maximum distance that the dual particle imager can be placed to still have good results? And the second question was, how does the algorithm know the distance to the source since it's just about the angles? I think
Cool.
those are probably pretty related.
Yeah. They're pretty intertwined. In terms of the effective range, I've personally done measurements with the H2DPI with sources up to 10 meters away. However, you have to take into account that while you can do a measurement at 10 meters away, your corresponding measurement time will probably be on the orders of hours unless you have a ridiculously strong source with a very high activity. Ultimately, it's going to be a combination of your source strength and your effective solid angle between your source and your detector that determines how long you'll actually need to measure to get a quote unquote good quality image. There's no real easy answer to really give in terms of, oh, how many imageable events you need to make a good quality image. It really often depends a lot on your actual geometries and your actual setup and everything. But in terms of the effective range, Typically, most of my measurements tend to be on the order of half a meter to maybe 2 meters away, since for a lot of the applications where you would want to use said HUDPI, that's kind of like the range that you're dealing with. Of course, in cases where, like in search scenarios where you have no idea where the source may be at and it may be meters away, that could be an issue. But one of the things you can do to resolve that is, say, have the HUDPI like on a moving platform, for example, such that you can get as close to the source as you can based, on figuring out count rates, differences, and everything. I will also note that there also is kind of a limit to the HoloLens range, since that's kind of independent of whatever the HDPI is sensitive to. At least with respect to the HoloLens headset, for that one, you're also looking at a effective range for the sensors of a couple of meters. But fortunately, the HoloLens facial mapping basically moves around you. So as you move around, your current built spatial map will also be added and updated as you see fit. So it's not too much of a big deal in terms of the effective range of the HoloLens in the mixed reality application. And to answer the second question about how far does the algorithm know that the source may be to the detector, it doesn't, which is why you basically need to give it a radius for the sake of the calculation of your spherical projection surface. Typically, I use a radius of 1 meter, since again, for most cases, I will be roughly in that general source of detector distance. The only times that could be an issue is for near field measurements. So say if you have a source that's like right up against the face of the detector, then that 100 centimeter or 1 meter radius would pose an issue, because it would basically make the simple back projection very much incorrect. So it would have to be changed. But generally speaking, it's not an issue if your radius isn't exactly what your source detector distance is. As long as it's within the ballpark or in the near vicinity, you tend to be fine in terms of the simple back projection. It doesn't have too much of an impact on, say, artifacts or just converging on the source location.
Great. So one of the other questions was, is the experimental uncertainty for this kind of imaging method normally around 10%? And if so, why?
Oh, no. From actual experimental data, it's quite a broad spectrum of ranges, actually. Typically, I want to say, to give you an idea, for a Californium source, the average uncertainty that I have, or the average relative uncertainty that I have for that measurement would be about between 25 to 30%. And the reason for that, generally speaking, the main sources of error or uncertainty in our measurements come from the Z position reconstruction and from the light output conversions, particularly when you're dealing with neutrons, since we use the Burke's relation to convert from neutron light output to neutron deposited energy. And it's, of course, the deposited energies that you use for all the imaging reconstructions. So if those have any degree of uncertainty, then that just gets expounded as you proceed with the projection process.
Nice. Okay, so the next one is, can your neutron imaging system image the distribution of neutrons that have scattered from items nearby to a source? So basically, what sort of like room return, how do you deal with that kind of situation? This continued, they said, I imagine the direct signal from the source drowns out any scattered, but what do you see?
Yeah, so that would be true. Generally speaking, for say a neutron image, for example, that has a couple hundred of events, imageable events, of those, probably over like 90% are actually just uncollided neutrons, so they're just directly from the source. Hence, they will dominate the final simple projected image, and anything you would really be able to glean from, say, scattering or room return would basically be washed out in the final image. Probably when you'd be able to most note the effects of, say, collided neutrons, like, or rather pre-collided neutrons that make it to the imager from, say, the floor, the wall or some other object in the room would be when you are dealing with images that are composed of very low imageable events or have very low statistics. That's honestly probably a good room return is probably a good reason why at low statistics the hotspot tends to shift a lot, because again, there's no guarantee that that incident neutron, for example, came directly from the source and collided. It could very well have collided, say, in another object before making it to the imager. I personally haven't done any any characterizations of these kinds of measurements, specifically looking at this kind of effect, say with like a shadow bar or something. But it could definitely be something that that would be interesting to look at in the future.
So can you use these imaging techniques with a potentially unknown source since the machine needs to know the incident radiation energy?
Yeah. So the idea is that you would use it for an unknown source at first. And then what you would do is you can bring up the gamma ray emission spectrum to get an idea of what peaks may be appearing, such that you can then constrain your imaging data set to a particular energy gate and thus tease out the actual radiation source location. Or at least that's what we'll work with gamma rays. For neutrons, it would be more so you just take whatever you can in terms of your neutron signature, since definitely out in the field and definitely outside of nuclear facilities, you really don't see neutrons out in the wild. So you ever even see neutrons, period, in a measurement, say like in a inspection kind of case, or like a specifically say like at the border, or whenever you're screening cargo or something, if you ever see neutrons to some degree above background, then that's already a cause for concern, because unless it's from one of the very few naturally occurring neutron sources out in nature or that are used commercially, chances are it would be in your best interest to more more closely search that particular uh, cargo or car or whatever. But yeah, in short, yeah, for example, you would use the HDPI for, say, getting a sense of what radiation sources may be present, since oftentimes you may not know ahead of time, and definitely in like search scenarios, so you may not have an idea of what's exactly gone missing. You just know it's something that has to be found, ASAP or whatever. But you can definitely improve your images, specifically your gamma images, if you already ahead of time know what you're looking for, so that you can better constrain your gates.
Right. And then I think this will probably be the last question because we've already gone 10 minutes over. So when you are looking at the test cases, how did you determine where to place those sensors?
Oh, it was just completely arbitrary, and I just came up with very simple test cases that would give very clear and easily observable cones, since I didn't want to go into some of the more you can get a lot more complex behaviors with the imageable cones. Like, for example, if they come at a certain uh, offset angle, then they tend to like get a bit distorted and stuff. So I just wanted it to be fairly nice and straightforward to understand, just to get the point across and everything. So nothing too complex or unusual for the test cases.
Okay. And I lied, there's only one question left. So in what kind of experiments would you want to actually stack the detectors on top of one another, like you had mentioned?
Well, so like in general, it would probably be for cases where you want a very compact kind of active volume, for example. Since if you want a portable system, you don't want the footprint of it to be quite large. So in terms of being optimal with your space or the volumes that you have available in an enclosed space, you may want to stack detectors. Otherwise, it would be to just improve your overall volume. Say if you only have access to 6 millimeter cubes or whatever, individually, they have small volumes, so you won't have quite that amount of high efficiency. But if you stack them all, you basically have a large volume to represent that. So that would be one example. But of course, there's a lot of other reasons why someone may want to do that, whether it be for specific design concerns on the engineering side or on the nuclear side, and of course cost concerns and other optimizations.
Excellent. Well, thank you so much for your talk today. I really enjoyed it. Thank you to everybody who is here listening as well. I believe that the recording should be available online on the MTV website for the summer school in the next few days. Thank you so much. Anything else that you had wanted to say real quick, Ricardo?
No, that's it. Yeah. Thank you
Right.
everyone for listening, and feel free if you have any other questions, and my emails on the bottom left of all the slides and everything. And of course, it should be, in all the emails and stuff. So feel free. Thank you.
Great. Thank you so much. See you all tomorrow.